Good morning, everybody. So it is my pleasure and my honor to introduce Rabah, as we work several years together. So Dr. Rabah BOUKHERROUB received his PhD in chemistry from Université Paul Sabatier in Toulouse in France. He is currently a CNRS director, research director, and a group leader in the Institute of Electronics, Microelectronics, and Nanotechnology, IMNs, that's affiliated to CNRS and University of Lille in France. He is an associate editor for ACS Applied Materials and Interfaces. His research interests are in the area of functional materials, surface chemistry, photophysics of semiconductors, material nanostructures with emphasis on biosensor, nanomedicine, photocatalysis, and electrocatalysis. He has co-authored more than 70 research publications, 700, sorry, yeah. 700 research publication, all is indexed. He wrote more than 40 book chapters and co-authored 10 books in the subjects related to nanotechnologies, material chemistry, and biosensors and nanomedicine. He has 15 patents or 50 patents pending, and his he or she index is 83. And last but not least, he has a great sense of humor. So if Rabah is there, I invite him to talk about the micro and nanotechnological advances in diabetes management. And I'm looking forward to his very interesting presentation.
Good morning, Yonya. Can you hear me?
Yes, we can hear you. And we can also see your presentation.
Okay, great. Thanks a lot for the introduction and good to see you.
I'm also glad to see you.
Yeah, thanks a lot. And thanks also for the organizers for their kind invitation. So it's really great pleasure to share probably the next 30 minutes with you on, I think the previous talk already was on metabolic diseases. And I think I will just indeed remain on that, but from another viewpoint. I think I will talk about diabetes, but how micro nanotechnology actually could improve diabetes management. And so it's mostly focused on technology, not on the bio aspects. Okay, so very briefly, I will just tell you where I'm coming from. I think it's in the north of France. It's an Institute of Electronics, Microelectronics and Nanotechnology, typically based on devices for telecommunications, for electronics. But as a group of chemists, we could still find our, I would say, place in this institute because we can really benefit a lot from the technology developed by different groups, but also with all our own technology as well, we can address some of the actual problems related to diabetes. Okay, I think the institute is part of these big platforms in France. There are 5: North, Southeast, Southwest, Paris, and Northeast. So this is really quite huge in a platform, about 1,600 square meters of clean room facilities and a lot of equipments and about 500 people. So there are different, you can see departments, 5 departments, 24 research groups, mostly in different aspects of macro and nano electronics related to acoustics, telecommunications, and electronics. This is the group. Our group, I think I will not focus really in the, what I want to share with you here is a group, almost half of chemists and half of biologists. So that's the reason actually we address, because we have biologists involved in diabetes, but we have also medical doctor, because you will see later on, it's really important to have access to patients to have the hospital. So that's really something we wanted to incorporate in the group, to have this, I would say, like something which is continuous from really scientific question to real application in clinics. Okay, so what we do in the group is really centered about materials, technology. And we have really expertise in developing nanomaterials, their functionalization to add the function to the material to make it specific for a targeted application. So you can see that there are different applications indeed in the group. Mostly we target either cancer, but more and more we shift to diabetes, and because we have people expert in diabetes in the group, but also because in cancer, I think there are cancers, but also there are a lot of groups involved. So it's very, very competitive. It's not we're trying to escape, but I think it's just much more complicated and there. Therefore, I think our main expertise is in the group is in diabetes, so we focus mostly on diabetes. So we have also developed a lot of nano formulations for antibacterial, antiviral, but also for aquaculture. And recently, indeed, we have actually created a startup on using nanotechnology to improve the nutritional value of planktonic species like copepods for aquaculture. The bottom part is related mostly for sensing, which could go as well up, but also for other type of research we do. But you will see, even though, sometimes it seems like it's very far away, it's not really. Here it's energy storage, because the aim to develop very miniaturized energy storage devices is indeed to all incorporate on the devices we prepare, and especially what the one I will focus today, for having something which is completely autonomous and we can use directly on our skin. Okay. So coming back to diabetes, diabetes indeed, as I said previously, it's really serious metabolic disease. And what is diabetes? It's nothing else than just a disease of sugar. It's having too much glucose in our blood. That's just typically what diabetes. So the scheme, what you see, I think it's really, I don't want to scare you, but I think what most of you think, there's a steady increase of diabetes in the world. And we can see by 2045, it's going to be about 51% increase. What I think what's really, astonishing numbers, it's those really related to Africa. You see it's more than 143% increase in the next, not even 20-25 years. The Middle East and North Africa as well. And as you can see it actually, obviously, when you travel in these countries, you can see indeed the number of this of diabetes compared probably just even like 10 years ago. I think it's really very, very a serious issue that should be addressed very, very seriously. And these countries really probably have to put a lot of money in research and development to address this issue. So when we talk about diabetes, typically there are different diabetes, but the most important one is type 1 and type 2. And type 1, I think it's the one probably you see the most, because it's indeed what people are having more insulin, and they have to inject insulin as people. Obviously, that's what you see. So we only think about type 1, but type 1 is really about 5-6%, not more than. Where we have really a lot of people with that, it's type 2 diabetes. In type 1, typically you don't have almost any beta cells. It means you do not produce any more insulin. Okay. Type 2 is still do produce insulin, but it's not enough to balance the glucose level in the blood. So that's typically, today we'll focus on type 1, it's indeed because it's the insulin. I think it's the most probably thing which is a bit, you can, type 2 still, you can actually, if you practice, you control your food, and you can actually, it's reversible still, but you can manage that. But I think type 1, there's nothing else than just injecting insulin. There is another type, but I think it is mostly specific for women. I think it's when they get pregnant, but normally often it disappears just after giving birth. Okay, so when we talk about the type 2, it's the most used actually drug today. It's what you call metformin. Often it's taken by oral, so it's easy, normally isn't a problem. Oral delivery, it's always convenient, it's pain-free, anyone can do it, but the big problem with oral delivery is often the destruction of the drug when it goes through the gastric acid in the. And also, if you use the yes, this is typically, yes, one of the biggest problems actually. It's the destruction of the drugs, although it's really an easy and convenient method of delivery. So the type 1, if I go back to type 1, that's the one which really requires insulin, the most effective way is this subcutaneous, it's using these injections. First thing, it's painful. It's for some people that have a phobia of needles, and also the waste of, of all these needles that could be potentially used for something else, and then you have the transmission or diseases. So there are other ways of using or delivering insulin to type 1 diabetes. There are some reported like pulmonary, nasal, buccal, and transdermal. Well, nasal and pulmonary, actually, they have been at some point on the market, but the products were just withdrawn from the market because it does actually cause a secondary effect. So today I will focus on something which is completely different, although yet, as I told you, it's really purely technological development. So you will see it's mostly science. It's nothing really actually at the, I would say, clinical level. So it's mostly still at the laboratory. It's really generating knowledge and mostly try to advance this way of delivery. So I will focus on patches, so how we can make a skin patch or mucoadhesive patch as well for using the mouth for delivery of insulin. So typically treating type 1 diabetes. Luckily, this is what I said, but probably more using the skin. So the idea is we had probably about 7, 8 years ago, whether it's possible to have a patch we can load with insulin, and then ideally, probably in the next few years, even having something you can insert like a glucose sensor, and all we can read at a given time the glucose level in the blood, and then act. It means we can inject through a very simple way, through a patch we can activate with either light or by applying a small voltage, and can deliver the insulin through the skin. So I think if you look at this, it's simple to draw on the hand, but I think it's much more complex and more complicated to put in practice. Okay. So what's the advantage of transdermal delivery? The advantage, certainly, I think the most important is the first pass effect of the liver. It means you don't metabolize the drug. It's easy, it's painless, so anyone can use it, if you compare to the injections. They are non-invasive, and also you can use them over a long period of time. So I think I will show you an example. You can even use it for up to a week without replacing the patch. So you can leave the patch really on the skin for up to 1 week. And it's simple and it's inexpensive because the patches I will show in my talk are quite cheap. I think it's almost worth a few, not even a few tens of cents. Okay. I think for the people you want, I think hopefully you stop smoking. If not, I guess I'm not sure. I'm not recommending the patches, but everyone knows that if you smoke at some point, you want just to quit. So what you do, you buy this nicotine patch. What is a nicotine patch? It's just simple. It's a patch which is charged or loaded with the nicotine. Nicotine is very small. You see here, it's a lipophilic. And it's low molecular weight. It's below 500 Dalton. So what do you do when you put this patch? Then the nicotine passively, without applying any stimulus, it will just diffuse through the skin. And that goes, indeed, you get enough nicotine in your blood. But what you do over time, you just reduce the amount of nicotine until you don't have any more of the need of nicotine. Okay? It's nice, it works, but unfortunately, it doesn't work for other molecules. It only works for very, very small molecules, and those are lipophilic. So if you put on the same patch, if you put insulin or any other drug, it would never cross the skin. Okay, so that's why indeed you have to actually provide a stimulus like light heating or electrothermal heating. And that's what you do. It's just you can open in very short times pores within the skin, and that also will allow to the drug to diffuse through the skin. Okay. The reason for that is if you look just at the structure of your skin, you have what you call this stratum corneae, which is about 15 micrometer thick layer. which actually prevents any diffusion of molecules through the skin. This is a good thing because it's the barrier. It's exactly what protects us from the environment. So it means if we don't have this, anything could diffuse through the skin, unless we have a good, really, I would say, immune system. We can just die if it's not the case. So this indeed is really nice because it protects us from the outside, from the environment, but also that's also a barrier for drug delivery through the skin. So yeah, in the talk I will address two types of everything here. Perfect. I will address the buccal mucosa and the skin. So the normal skin on our hand here and in the mouth. The reason that the difference is when you look at the thickness of the mucus here, it's about 300 to 500 micrometer, and the skin is quite thicker. Okay, so indeed, it's much easier to deliver through the mouth than through the skin. You will see in two examples indeed how it's, but each component, of course, has its own advantages and limitations. In literature, there are a lot of other ways of doing it. So, and this you can, indeed, this type of devices you can buy and can purchase in literature. It's using either through applying either an electrical current or ultrasound or a high voltage. You can actually generate the pores through, and you can deliver through the skin. All this is really techniques are not useful and most of the time abandoned because they're just harm and they can cause actually to burn the skin. I would say the most really exciting and most interesting approach is that using microneedles. Why using microneedles? And it could be actually made out of polymer. It means it's something which is mechanically suitable for, it would not harm the skin, but because this is a very small needles, they can go through this starting corneum, so they can cross this starting corneum, and they can deliver indeed any drug. I'm not talking about, although they were used also for insulin. The only problem we have with these microneedles is it's a one-goal use. It means when it crosses, the microneedles often will dissolve and will release the amount of the drug in once. It means you don't have a control. It's just a burst. You don't have a control on the amount of the drug you release. And also you cannot reuse these microneedles. So having said that, I think it's just now, is it possible to make something? We can use the skin, we can use light or electrical voltage to open the pores on the skin and then be able to deliver insulin. So the first example, I will start on using near-infrared light to activate or to generate heat on the skin. The reason we use near-infrared, if you look at completely the top right figure, there's a window here, what you call a biological safe window, with about 980 nanometers or 1 micrometer, where nothing absorbs, neither tissues or cells or biological molecules. So if we can use a patch that can absorb the light here, we can have something that can, the light will be absorbed only by the patch and generate heat, but so I will not harm the tissue or my skin. Okay. So for that, what we choose, indeed, we choose to use graphene. It's a carbon-based material. Why graphene? Graphene is this material that can absorb light and can transform the light to heat, and very, very efficiently. And you can see it's a black matter, so it means it can absorb the light from any wavelength. So we can use really the 900, 800, even more, any almost excitation wave. So this work we have performed this work with a colleague in Turkey. The reason he is most has a technical expertise in making polymers, and we want to use these polymers, gel type polymers, and put the graphene inside as like nano heaters. It means you have a matrix polymers, and inside you have small nano heaters. So it's really an easy way of making it. It's just UV polymerization of this small molecule, and then you have this graphene different percentage really, but we'll have to optimize that. We'll show you later on. You see, if you can make the polymer without graphene, it's quite very transparent. There's no bottom, but when you put the graphene inside, you see it becomes black. So it means you can absorb light from any wavelength, which is really important. Another aspect is this being porous. It's very, very highly porous. It means you can really store a big amount of insulin inside. And because it retains a lot of water, and that's exactly what you need for any biological molecule, you will have any denaturations. It's stable. You can heat it up to 250. It's an organic material, but of course, we never heat up the material to 250. We will mostly heat about 50 to 55 degrees C. So when you look at this, I mean, we have all the features for an irradiation at 900, like 1 micron, whatever you want. You have big amount of water in it. It's porous. It means it can load a big amount of water and is thermally stable. So next, what we have looked at is how indeed the amount of graphene in the polymer will impact on the heating properties. It means now I come with the light at 980 nanometers, sorry, irradiate this polymer containing graphene, and I record with a camera, an infrared camera, the increase of the temperature. And you see nicely that this material heats up almost to 70 degrees C, and using even a very small laser power of 0.7 watts square centimeter, you can see that I can reach, about 70, 71 degrees. So it has absolutely everything to operate under a laser, which is of low power. So normally I should be able to do something with it. So what you can see now, that when I load insulin on this patch, and they put this just passively, the insulin is nothing coming out. It means the insulin is retained inside the polymer matrix even after 1 week. However, now if I irradiate with the laser for 10 minutes, I can release the insulin. And I can do that almost every day. So it's really like a reservoir where I have insulin. I can release the amount I want just by controlling the time of irradiation. And I can do that over a week. That's the reason I told you can really use this patch for a week without any problems. Now, the most important thing is the insulin I have in this patch, in this polymer matrix. When I release it, is it still active? And because if it's not active, it cannot really go further. That's it. And indeed, what you see then we have is just this assay, biological assay, just related to the phosphorylation of this protein. The insulin that is released under photothermal conditions, it's even more active than the normal insulin, the native insulin. And this is definitely a fact. I mean, we have done this for 20, 30 times. It's always there. We don't have an explanation about that, but definitely the insulin that has been released from this polymer, it's much more active, well, slightly more active than just native insulin. Now, like it was actually stressed before, we cannot just go and work on the skin, human skin, so we have to find an alternative for that. And this, what we use, what you call it, this is when it's a pig ear skin, because it resembles more the human skin, but also we can have it for free from slaughter. In Valenciennes, we can have as many as we want, and it's much easier to work with the pig skin in the lab. For human skin, we cannot anyways work with it. So before going further, so we took the skin to check if indeed it's about the thickness, it's about 1 millimeter. We use this France diffusion cell, and we see if we put here now the skin, we put on top of it the patch, which is loaded with insulin. We irradiate with the laser at 980 nanometers for 10 minutes. And then we can actually see if this insulin goes through the skin, and we can quantify that with HPLC or UVs. And what you see indeed, like we say in French, it's a glass which is half full or half empty. Half empty is because, no, half full, I would say first. Half full because you have very nice kinetics. It means the insulin goes through the skin, and you can see it with the fluorescence here when we actually label the skin with the fluorescent molecule. You see that you have pores here generated, and you see that the skin goes all over through the skin. They have very nice pharmacokinetics here, but it's very slow. then the glass of it is half empty because you cannot use for diabetes. I mean, it takes almost up to 2 hours to get to and the flux is not really high enough. So yes, but this is the first demonstration that we can use light to induce drug delivery or insulin delivery through the skin. Further, and I will show you that we can, after a few years, of course, to understand better what's going on, we can even go further, and now we can apply just a voltage to generate heat. And applying a voltage, we see that I can reach a temperature which is about 55 degrees C in less than 3 or 4 seconds. It's very, very quick. And then now I compare actually on real samples. We did this with the mice, and we can see whether I use this subcutaneous injection or I use this electrothermal conditions, I can reach exactly the same. I can regulate the glucose level. So it means I can inject exactly the same amount of insulin through the subcutaneous using an injection or using this electrothermal patch. I think I have probably another 2 minutes or.
Yeah, it's fine. 2 minutes is fine.
Yeah, 2 minutes, and I will. So this now, I think, yes, this we can show indeed that we can use electrothermal. It means we can apply 1 volt. It's really nothing on this patch for a few seconds, and you open up pores and you can inject the insulin. So this is really something which is promising, and hopefully we can drive it further to the clinical application and it really like on a big, which resembles most the human. Now I would just very quickly show an example on also using patch in the mouth. So I will skip all the type of materials we use. It's really simple and easy. And the characterization. And again, as I told you previously, the importance of the mouth, because the barrier is much smaller, it's much thinner. So now we expect indeed to have an easy way of delivering the insulin. It works. It's not working very nicely. Why? Because actually now the problem is that we have the insulin which is in tract. It doesn't mean it's released, but it stays within the patch. Otherwise, yes, it works the same way. You can see it as well that with the fluorescence that the whole insulin actually goes through. So both are really, I think, are promising. I would not focus this, but what we do is this is really, I would say, it's a real patch we put in the mouth. I mean, this is not an animal; it's really student. And also, then what we do, we go a little bit further, and we use patients at the end, volunteers, to give us really a feedback on this patch, whether it's possible or not to implement this patch at the clinical level. So, then you go to other questions about the taste, the comfort, it's the addition time. So really, it's a very nice experience to look indeed at the people, how they when you have a new biomedical device, how they respond. Just it's not on the clinical level, but it's mostly how they accept this patch. And so this is very nice. Of course, it's done only about 6 volunteers, but the idea and this then later on to go probably above 20 or 30 volunteers to have a feedback and how we can improve also the. This is just, I would say, the aesthetic aspect of the patch. I will stop here. Then indeed this type of now we work on also to making macro needles out of polymers and graphene, and we can also apply this type of photothermal patches for healing. This is wound healing, and it works very, very nicely. And I think I will just stop here. And thank you for your attention. And if you have any questions, I will be very happy to answer your questions or any discussion or comment. It will be helpful to take that out. Thanks a lot.
Thank you, Rabah, for this very nice and interesting presentation. I would offer as a volunteer if I would be there. So maybe in the future.
We don't pay you, yeah.
Yeah, I know. So if there are any questions from the audience.
Thank you. I want to congratulate for your nice work, and I think this is a very nice idea this to couple the sensor with a reservoir for drug, any drug, doesn't matter. It's a very nice idea, and we will think about it. Thank you very much.
Thanks a lot. Yeah, thank you.
Is there any other question? There is a question from the audience. Okay.
Thank you very much for the very nice presentation, and of course of actuality, because diabetes is indeed a problem. You talked about a heat triggered delivery, but you are talking about insulin, which is let's say a thermosensitive molecule. Which is the temperature of the triggering, let's say?
Yeah.
Thank you.
You're welcome. Yeah, thanks. Yeah. Well, I can only respond, I think, not fully to this question. So what we know, the difficulty, what we do, indeed, when we have the patch, we irradiate or we apply a voltage. So what's the temperature we measure it on the surface. It means we don't know exactly what's the temperature inside the patch. So all I can tell you, indeed, the surface temperature is about 50 to 53 degrees C. And this we can control because we know it's just a distance. So we can control the laser power density and the distance. This we can control without any problem. What we don't know, indeed, is the temperature inside the patch, but it doesn't seem it's problematic because the patch, it's only the surface which is in contact with the skin. And it seems we have looked for the biocompatibility. We looked at the damage of the skin. When we expose for continuous irradiation of the patch in contact with the skin, there's no problem.
Okay, thank you very much.
Welcome.
Bye-bye.
Is there any questions from the online participants? No. Okay, thank you, Rabah, so much for this kind presentation. We will continue inviting you to these events.
Thanks,
you so
Joanna,
much.
for the kind invitation. Thanks a lot. Yeah, thank you.
You're welcome. Have a nice day.
You too.